Yeah. So, all right, let's make sure we're live here on the iPad. Oh, this is great. It's not as taking as much room as the other thing. So, all right. So let's see. Where were we? Last time we basically started to construct a full addition unit for an 8-bit ALU, and uh, essentially what was the idea, right, is that you just have to do everything bitwise, and the way that we constructed it was with what's called a ripple carry adder, because the the final state of the addition, okay, um, depends on all 8 bits, right? But the later bits are going to possibly have their state change based on a carry from an earlier bit, and since the each addition circuit is made up of what? In the case of the half adder, 2 gates, and in the case of the full adders, what was it, 5 gates it took us, right? So it's not going to be an instantaneous transition, but it will be pretty dang fast relative to our clock speed. Okay, so if we made our clock speed too fast, then we might get in the situation where we'd read from the result bits before they had actually finished settling down to their correct values. Um, and yeah, so don't do that basically. Um, but you know, for simulation's sake, we're going to make our clock speed super slow, of like 1 hertz, and we don't have to worry about this because the speed at which the transistors and stuff would be switching states is like milli to nanosecond kind of time scale, right? Whereas if we're that, you know, which is what, a factor of 10 to the 6 to 10 to the ninth difference from what our cycles are, right? So like it's not going to be a problem, right? Okay, so good. So the last, well, okay, and then we talked about what are the other operations that the Brookshire ALU can do or needs to be able to do. Well, what were the other logical or arithmetic operations that we had? We had adding as integers. Okay, the Brookshire architecture does define adding as floats, but let's just ignore that because 8-bit floating point is stupid. Okay, but aside from that, what else is there? Huh? There's no hardware multiplication though. Okay, so nor subtraction for that matter in Brookshire. Now, if we were to make a real ALU, okay, so like say a 6502 class ALU, there is a hardware subtractor. There isn't in Brookshire. Okay, which is why you guys remember, those of you who are in 101, remember how did we do subtraction? You had to do the 2's complement stuff, so you had to flip the bits and add 1. And so subtraction took like 5 or 6 instructions to actually accomplish because you had to, you know, do all that stuff step by step. Okay. Now, a real ALU, like even the 6502, has a hardware subtractor. And how does it look? Well, basically, the idea is kind of like what we had for the addition circuit that we built last time. We defined a subtraction circuit that instead of carries, what does it use? Right? So when you do subtraction, like when you add things, you carry to the next place. Yeah, you'd have to borrow from the previous position if the first number, the thing that you were subtracting from, had a 0 in that place, right? So the circuit wouldn't look exactly like it would for the addition circuit, but it would be kind of on that order in terms of the complexity. Okay, so we could build that, but the Brookshire architecture doesn't define a subtraction operation, so let's just pretend that that doesn't exist. okay? Because we could build it out of the addition circuit with other stuff. Okay, what else was there? Okay, bit shifting, which in Brookshire was actually bit rotating, not bit shifting. Okay, so what's the difference? If you bit shift and there's somebody on the far end, what happens to him? He falls off the boat and he's gone. In bit rotation, what happens to a dude on the far end? He comes around back to the other end, and if there's not a sound effect when you do that, then it's wrong. I'm sorry, and you fail. Huh? That's a good question. Let's see if there's something in the input-output menu that would accomplish a sound effect. Well, we've got LED, RGB video. I bet you we could hack something in there. Here's the thing that I really, really want to figure out exactly what it is and why it's called that. The Reptar local bus. Okay, now especially because I bet you there's a reason that it's called Reptar. And what is that? You guys are probably too young to get this. Huh? Rugrats, yeah. Okay, so there's this cartoon on Nickelodeon. Okay.
How do you remember that?
What do you mean? Well, because I was a little older when that one came on the air, and um, my sister liked it, but so we'd put it on. It would be on the TV, and I would right because there were a couple of them that you know I was too old to be watching Saturday morning cartoons, but my sister wasn't, and so I kind of got them through her. Like let's see, that one got added, and also Rocco's Modern Life. Yeah. So my dad and I still make jokes based on Rocco's Modern Life. Like, you guys remember the plumber in Rocco's Modern Life? Like, the back of his pants are always falling down. And he's like, "Could you get that? Thanks a lot." And, um, yes. So we still quote stuff from that. But yeah, Rugrats. So there was this dinosaur character. It was like a show within a show in that thing called Reptar. And then there was an episode or the movie or the Rugrats movie where they like go to see Reptar on ice, and it was like a you know ice skating musical with Reptar, and yeah. Anyway, Reptar on ice. No, I do not. I just have. If you guys haven't figured this out, I have a lot of very very specific recollections of the past. Right. So anyway. Okay, so I bet you that the Reptar is some sort of a joke on that, but anyway. All right, so it doesn't look like we've got audio out here, but you guys can make the sound effects. Yeah. All right. Well, I mean, Logisim, it's open source, right? So we could go in and add it. So okay. Anyway, um, so what other operations do we have though besides the addition? We had, well, rotation, which we need to get to. That's going to be fun. But we also had logical and, logical or, and logical XOR. Now, those are the easy three because how do you XOR 8 bits together with a different 8 bits? You just do it one bit at a time, right? So those guys are super easy. It's just going to be for, say, XOR, 8 XOR gates, and bit 0 goes with bit 0 and outputs to bit 0 and bit 1 with bit 1 to bit 1, right? You do it bitwise. That's super easy. Yes? Okay. All right, so the fun one is rotation. And for this, I'm going to show you guys a really cool trick. Rotate any bit with this one weird trick. Now you like internet ads, right? And now I need like a picture of a banana that's going overripe. Yeah, okay. Um, well, then that'd be like Flex Seal, where I've got like a leaking barrel full of water and I just slap it on and I cut this boat in half. That's the thing that would be really funny. So physics, Lillis, like for your ad lab project, you need to do something like that. Be like, let's see all the ridiculous stuff we can do with Flex Seal. Um, anyway, um, okay, so let's talk about rotations versus shifting. Okay, so the Brookshire architecture only defines bit rotations, not bit shifting. All right, so what's the difference? Okay, that if I shift a number, like let's say I take the bit pattern of all ones and I shift it one position to the right, what is going to be the resulting bit pattern? Yeah, exactly. Okay. Now, this actually brings up a distinction because there actually are two kinds of shifts that we could do. We could do logical or we could do arithmetic. Okay. And the difference is that uh, if I do a logical shift, what would the far left bit be of all ones after I shift by one position? It'd be a zero. If I do an arithmetic shift, what should it be? What do you think? Well, there's only one other option, right? Okay, it should be a 1 in that case. And why? Because what is the bit pattern of all ones? What does that represent as an integer? It's it happens to be -1, but forget the fact it's -1. It's definitely negative something, right? Okay, so if I want to do an arithmetic shift, then I want to keep the sign bit, which was the far left bit, the same as what it was with my starting number. Okay. And the reason I'd want to do that is because if I do if I do a shift, right, if I take a bit pattern and I shift everybody to the right by one position, what is that tantamount to doing arithmetically? It's dividing by two and of course, discarding the remainder. Well, if I take a negative number and I divide it by two, the result should be still a negative number. Yes? Okay. So that's the difference between a logical and arithmetic shift. Now, to some extent, that's an artificial distinction for our discussion today because the Brookshire doesn't define either of them, right? What it defines is a rotate. Okay, so let's start building the idea for a rotation circuit. Okay, so what do I need to do? I need to accept in an 8-bit number, okay, and that's the thing I need to rotate. I also need to accept in, well, in the Brookshire architecture, how many what was the opcode for rotating, right? Or sorry, what was the full instruction for rotating? It was AR0X. Okay, so it was A meant to do a rotation. R meant which register am I rotating? Well, that's 0 through F, one of them. Okay, the 0 was hard coded, and the X was how many places to the right you did the rotation. Yes? Okay, so that X, how many bits encoded the rotation amount in Brookshire instruction? How many bits? 4 bits. Okay. So what I want to do then is I want to accept in, oops, 4 bits, which will be my rotation amount. Okay. So let me call this the input, and this one is going to be the rotation amount. Okay, and I'm going to need some splitters. And as you guys will see in a moment, I'll actually need another one there. So let me make this one. I need a fan out by 8, and I need bit width of 8. like so. Okay, and then this is where it's going to get fun and messy. Okay, so I want to be really smart about how I do this. Okay, and in particular, what does your gut say in terms of building a rotation circuit? Should you build 7 circuits, or 8 rather? Rotate by 0, rotate by 1, rotate by 2, rotate by 3. I mean, couldn't we do that? But that would be unnecessarily complicated. So what I want to do is I want to build something that rotates by any amount, but does it with one single circuit, or, okay. All right. So, um, hmm, okay. So, okay. So you're on the right track there, right? If you rotate by, say, 3, how could you do that? You could do a rotate by 1, then another rotate. So, like, you could think of this iteratively, okay? But let's go to the second thing that Evan said, which was, let's say that you'd made a rotate by 1 and a rotate by 2 and a rotate by 3. Well, then how could you accomplish, like, say, rotating by 7? Okay, right? Do 3 twice and then 1. All right, let's think about a different way to break this up. I could do 1 7 times. Yes, that's true. Yes, you could. Okay. So you're saying do 1 and 3. Okay. Could you split this up another way? All right, here's what I claim we should do. We should do 1, 2, and 4. Why? Because base 2 binary, right? Every binary number can be written as a combination of 1s, 2s, 4s, and so on, right? Now, in this case, if we're doing an 8-bit rotation, or we're rotating an 8-bit number, if I rotate it by 8 positions, what happens? Absolutely nothing, right? That's the same as rotating it by 0 positions. So do I actually care about all 4 bits of my rotate field here? No, I only care about the least significant 3. Okay, because rotating by 9 times is the same as rotating by 1. So I don't care about that far left bit. Okay, so what this means is that here I'm going to do 4 bits fan out by 4, but this bit I don't care about. It doesn't matter. Okay, the other 3 are the ones that I want. Okay, so I need to construct a rotate by 1, a rotate by 2, and a rotate by 4, and I'm going to put them sequentially, okay? Because rotating by 6 would be rotate by 2 and also rotate by 4. Okay, does that kind of make sense how I'm being really clever here? Yeah? Okay. All right, so let's see, which way do I want this? Okay, so I'm going to do this. Oops. I can do this with 2 or with a bunch of plexers. I can do it with a bunch of multiplex. Oh, sorry. Damn it. Come on. There we go. demultiplexers, or I can do it with a bunch of multiplexers. Let me just do, I'll do demultiplexers here. Okay, let me just do it for 4 of them, and I think you guys will start to get the idea. Okay, well, actually, no, I need all 8 because otherwise you won't see the pattern. Dang it. There we go. Okay, so this will start to get a little bit messy, but all right, so here's what I'm going to do. Output inputs 0 to 0. Well, I should probably make more space than that. 1 to 1, 2 to 2. Right, okay, so this part is I'm just connecting these guys. Hoping I left enough space. Okay, then the other thing I need is, let me pipe this around. I'm going to move this rotation thing down, or the bit part down here, and I'm going to connect this here, and all of the selectors I'm going to connect to that bit. Okay, so now the output of this is, oh wait, do I want, hold on, I think I might want, yeah, sorry, I wanted multiplexers, not demultiplexers. All right, let me delete all of this and start over. Sorry. Um, while I'm doing this, I'll just mention briefly that um, when you guys are using Logisim, I put it on the Pis, and I think I showed you guys how to launch it last time or 2 times ago, whatever. Right? You have to do it through the console, Java space dash jar space, and then the thing. Um, but because it's just a Java thing, you can run it on any computer that's got Java on it. Um, so you don't have to run it on your Pi. No, it's not, right? But it all you have to do is download the jar file from Canvas and then just run it. So I think all the school computers should have Java on them, the Java runtime, right? So yeah, just download it, run it, and it should be fine, right? And I put a copy of the jar file for this version 3.3.0 on the Canvas page, so you guys can grab it there. Okay, so sorry, I wanted multiplexers, not demultiplexers, and we'll see why in a second. Hmm? No, that would be nice, but alas. Okay, so um, here's what I'm going to do, right? And in fact, let me scoot all these guys up a little bit. Let me zoom out a bit. Scoot all these guys up. Okay, so what I want to do is the way I'm going to think of this multiplexer is I'm going to think its output is going to be, okay, whatever. And remember what a multiplexer does is it selects which inputs get connected to the output, okay? And in this case, I'm going to use a 2-to-1 multiplexer. So if I'm rotating by 1 bit, I'm either rotating by 1 bit or I'm not, okay? So that's why I'm going to use 2 inputs here for each of these. And then for rotating by 2 bits, I would have a second array of 8 of these, and for rotating by 4, I'd have a third array of 8 of them. We'll just start with the 1-bit rotation. Okay, so I either rotate by that many bits or I don't, right? So if I don't rotate, then how do I connect all this stuff? 1-to-1, 2-to-2, and so on. Yes? Okay, so that would be to do absolutely nothing. Okay, and here is where I didn't leave myself enough space. I need to scoot this to the right by a little bit. Okay, now, if I wanted to rotate by 1, then who gets connected to whom? If rotating by 1 to the right, okay, because that's the other thing, which direction do the rotations go in Brookshire? It's only defined to go to the right. So if we wanted to do a rotation to the left, we had to do the mental gymnastics to say, oh, rotating by 3 to the left is the same as by 5 to the right. Yes? Okay, so there's no hardware option for doing the left-hand rotations. Okay, so if I do a rotation to the right by 1 bit, okay, who gets connected to who ends up in bit position 0 if I rotate by 1 position to the right? Bit 1, okay, and then the last thing is, where does bit 0 end up? All the way around in bit 7. Yes? Okay, so if I'm rotating by 1 position, then this is how they'll get connected. 1 to 0, 2 to 1, 3 to 2, 4 to 3, 5 to 4, oops, 6 to 5, and 7 to this guy. Okay, and who gets connected here? Number 1, he comes all the way around. Okay, so then I'll just do this. Okay, now I need to connect my bit selector to everybody. Like so. Okay, so let's pick a bit pattern just for sake of demonstration. Okay, and then the other thing is I need an output. So let me take a splitter, and then I want, in this case, I want an 8 fan, 8 split, but I want this thing facing the other direction so I can group everybody back up. Okay, so my output would be 0 to 0, 1 to 1, 2 to 2, 3 to 3, and so on. Okay, so this part's just doing the wiring. Right, it's kind of boring. Okay, and then let me put an output pin so we can actually read the answer. Okay, so right now, how much have I rotated by? 0, okay, and that makes sense because this guy down here, in fact, let me move this so that we can see it better. Let me move this up here so that we can see all of them at the same time. Okay, and I don't need to keep dragging this guy around. Okay, so right now I'm rotating by 0. Okay, so not shockingly, what's true about the output versus the input? They're the same thing. Okay, if I wanted to rotate by 1 position, then I would set the far right bit here to be a 1. Okay, and if I do that, what's going to happen? All of the multiplexers are going to select the, instead of their 0th input, which is their top input, they're going to select which input? Their bottom input. Okay, so if I click this right here, what happens? Okay, all of the multiplexers switched from doing their top input to outputting their bottom input. Okay, but I had wired the bottom inputs so that they were 1 bit off from the actual input, right? And then now look at the pattern. Is that 1 position to the right? Yeah? Okay, now to really demonstrate that we got this correct, let me take, let me make the bit pattern that, right? So what happens to that 1 that's on the far right? He rotates around to be the 1 that's now on the far left. Okay, does that make sense? Isn't that kind of clever? Okay. Huh? Yes, because we're rotating, we're rotating this way because, so look at the splitter that's on my input. Who's at the top? Bit 0. Which bit is bit 0? The far right bit, okay, because we start counting with the least significant bit and go to the most significant bit. Because we're doing this as Little Indian. 0 goes all the way down to 7, which is yeah, okay. All right, so you see how the second input for all of the multiplexers is just 1 off of the first input? How would I change this to make it a 2 off or 2 rotation? Okay, so here I've got 1 goes to 0, 2 goes to 1, and so on. Okay, that's for a 1-bit rotation. How would I do this for a 2-bit rotation or 2-spot rotation? They'd be off by 2. So 2 would go to 0, 3 would go to 1, and so on. Okay, where would 0 go? Around to 6, and where would 1 go? Around to 7. Yes? Okay. What about if I wanted to do a 4-spot rotation? Well, 0 would go around to 4, 1 would go to 5, 2 would go to 6, 3 would go to 7, 4 would go to 0, 5 to 1, 6 to 2, 7 to 3. Okay, so it'd be like this, but just offset by 4 spots instead of 2 spots instead of 1 spot. Okay, does that make sense? The idea, anyway. Yes.
All of them together, we would take the output from the first one, and that would be the input.
Exactly. We'd pipeline it. Okay, so if we were to build the 4-bit, or sorry, the 2-bit rotator, I would put that here. And what are the inputs that I use for it? I'll use the inputs that are the outputs from the previous stage. Okay, so because how could I think of, say, let's take, for example, rotating by 7. That's rotating by 1, then rotating by 2, then rotating by 4. Right, so I'm taking taking advantage of binary encoding to build my circuit. Does that make sense? That's kind of crazy, I realize. So this thing is called a barrel shifter. Barrel is in, like, yeah, Donkey Kong. Okay, I guess, right? Huh? Yeah? Okay, isn't this kind of clever? Right? All of this just crap load of little multiplexes, and they're all 2-to-1 multiplexers, which are relatively simple in terms of the number of gates it takes to do it. Okay, so that's sort of the start, right? Is I've built the 1-bit or 1-spot rotator. We'd have to do the same idea for 2 and 4 and then stage them together. Okay, and then who would control the multiplexers for the 2-spot rotation? Bit number. So if the 0th bit controls the 1-spot rotation, then bit 1 controls the 2-spot rotation, and bit 3 controls the 4-spot rotation. And what's controlled by the 4th bit there? Nothing. I don't need it. Okay, because rotating by 8 positions is the same as rotating by 0. It doesn't actually do anything. Okay, does that make sense? Yeah, so that bit we just discard. What this means, by the way, is that, well, let's think about the Brookshire encoding for this instruction. It was A, register number, okay, those parts we can't change, 0, rotation amount. What could we have then done? Well, what about if we made left rotating to put a 1 where that 0 is? Okay, and what about if we defined a shift instead of a rotate? We could have complicated up the Brookshire instruction there to get more operations because we were wasting 4 bits worth of the encoding otherwise. Okay, so I think I've told you guys this. Like, I want to sit down and well, build/define Brookshire 2.0, and this is one of the things I would do is I would make the rotation command be able to do left or right, and do arithmetic, logical, and rotate. Do all 3, right? Because I would need 6 encodings for that. 3 for the left versions and 3 for the right versions. And I've got 4 bits to work with. Well, that's how many patterns can I get out of 4 bits? 16. And I just said 6 things, right? So that's kind of nice, right? I've got 10 more, right? It's going to be like Oprah, right? You get a bit pattern, and you get a bit pattern, and everybody gets a bit pattern. No? Okay. All right. So that's a barrel shifter, or the start of a barrel shifter anyway. Kind of cool? Yes or no? Okay. All right. We talked about and, or, XOR, and so on. Okay. So the next thing I want to show you guys is how we can do some timing circuitry. So let me go back to me save this, and let me call this, just say, oops, just call this barrel, whatever. All right, so I'm going to make a new circuit, and I'll call this like timing thing. Okay. All right, so what I'm going to do is let's take um, let's take the hypothetical example of if I wanted to add two numbers from memory. Okay, so what's sort of the cycle of operations? Well, I have to read in the instruction from memory. That's step one. Okay, a decoder would be just the circuit to decode it. Okay, so let's say that the operation tells me to add two registers together and then write the answer to a third register. Okay, well, the first thing I got to do then, so load in the instruction, step one, load in the first number from the first register into the ALU, load in the second number from the second register to the ALU, then add them. Take that answer and pipe it out and write it to the correct destination register. And then I'm finished and I'm ready to move on to the next instruction. So that took 4 steps, okay, or 4 cycles. Okay, so how could I make basically a circuit that will tell me or what I can use to time which step I'm in? Okay, this is also really clever. I'm going to need a clock. That should come as no surprise. Yes? Okay. Then I'm going to need a pin here, which I'm going to call reset. Okay. And then I'm going to need a bunch of D flip-flops. Okay, so I'll just do 4 for sake of example here, and I think you guys will get the idea that I could do this with certainly more. All right, so I'm going to put these guys in order here. Okay, and I'm going to connect each of their outputs to the previous input. And then the dude at the end, I'm going to come around and wire him here. Okay, they each need a clock. Okay, so I'll put the clock circuit, the clock part here. Okay, and this little arrowy symbol thing there is the symbol for clock. So if you see that little thing on any dude, any circuit component, that just says, hey, that's where I want the clock plugged in. Okay, no big deal. Okay, so they've all got a clock. And then this reset pin, I'm going to connect, and this part is going to be a little funny. The R on all of these dudes is reset. And I'm going to connect the reset to all but the first one. But then I'm going to connect the reset pin to the set on the very first one. Okay, so first off, Lynn, let me just let me start ticking. Okay. Wow, Dr. McKinney, that's a really exciting circuit. Okay, but watch what happens when I set this. Huh. Isn't that kind of cool? Okay. You need some explanation? Well, huh? Why did I turn off the reset? I did. Yeah. Yeah. And I mean, if I wanted to doctor this thing up, I can make it sort of do that automatically so that I don't have to sort of initialize it. Um, right? I mean, because one thing I could do there, right, is I could say, okay, take all of the outputs from all 4 of these things, and if all 4 of them are 0, set the reset. And if they're not, then don't do anything. But if they're not, that means the circuit's already sort of been activated, if you will, and I don't need to worry about it. Okay, so yeah, but I would need the reset thing here. Okay, so what's happening, right, is that on each rising edge of the clock cycle, that's when, so a rising edge means when the clock goes from 0 to 1, so it turns from dark green to light green, okay, is when everybody is going to change state. But they're going to change state based on what's their input, which is what's connected to the D on the each thing. Well, all of them have a 0 behind them, except for one of them, which is a 1. And so the 1 sort of cascades down the chain. And because I looped it back around to the end, when the process finishes, it just sort of starts all over again. Okay, so this is called a ring counter for obvious reasons. Okay, and I can make the ring counter count however many things I want just by using the appropriate number of D flip-flops. Okay, so in this case, 4, right? So what I could do is I could say, all right, I'm going to think of this output as step 1, step 2, step 3, and then step 4. And then I could say, okay, which step am I doing connects the sort of thing that activates doing that procedure to the output of the appropriate step in my ring counter. And then I can keep all the reptars dancing in synchronicity. Yeah, the little ring. Yeah, here. Okay, so that the output's low. Yeah, so those the little ring is the universal symbol for negation. So each of these flip-flops actually has 2 outputs, and you'll notice that the bottom output is always opposite of the top output. So if for some reason you needed the gated output, you can get it from the bottom without having to pipe it through another NOT gate. Okay. In this case, did I use any of those outputs? No. Okay. Huh? Well, I could, right? But um, yeah. So there, who would be moving, so to speak? It'd be all ones except for there'd be a one spot that's a 0 that sort of cascades. Okay, I don't know why we would need that, but I mean we could, right? We could certainly use it if we wanted. Okay, so this is basically the fundamental or a fundamental way to build a timing circuit, right? So that I can keep sort of sequential operations in lockstep. Okay, um, and well, if I can build this with 4, I could build it with however many I wanted, right? So if I had some squirrely operation that took, I don't know, 7 steps, right? I could do this. I could build one of these with 7 gates, one of them with 6 gates, and so on, or 6 flops, not gates, uh, and then have a counter. Okay. All right. Does this kind of make sense? Yeah. Kind of clever. Um, Using something sort of like this, I could also build a clock divider, right? So if my clock is operating at 1 hertz, could I build a circuit that outputs at half a hertz, a 0 or a 1? Yeah, I could just throw in a second clock, but which is on Logisim probably what I would do. But you can do clock division if you're clever. And a lot of these, right? It's not like this is patented information. This little idea here, right? You can Google and find any of these sorts of clever tricks. and they're kind of, in fact, I was just looking at something yesterday, which was a self-initializing, because here I had to sort of initialize it from the get-go by doing the set thing. Um, and, I might want to be able to reset it at any given point. Okay, that's fine. But I could build something that does sort of self-initialization if I wanted. Okay. Okay, so does that kind of make sense? Yeah? Yes, Lilith? Yeah, so it'd be like, well, it depends on how we build the machine, right? Because, for example, let's say the halt command in Brookshire. Does the halt command require multiple steps? No, we could just tie it straight into the clock, right? Because you halt and that's the end of it. Okay, but the something like an ALU operation where I need to take in two registers values, okay, then do the operation, then write back to the register, right? That's going to take several sort of sequential steps depending on how I set things up. And um, um, so depending on how many steps that takes, I would need a counter of the appropriate length, right? So like, let's say, for example, that doing addition of two registers took, and I'm just making up numbers here, took 4 steps, but doing the rotation only takes 3 steps, okay? Or 2 steps or something, right? Then what kind of counters would I want? I'd want a 2-step counter, and I'd want a 4-step counter, and I'd want to connect the appropriate stuff to the appropriate stuff. Okay, now I'm really sweeping details under the rug when I say appropriate stuff and inappropriate stuff, but you guys will forgive me, right? And we'll start building some other things, right? Okay, so does that kind of make sense? Sort of? Okay, so let's start thinking about a computer, building a computer in this thing, sort of schematically, right? What are the big boxes that we're going to need? Well, we need, so let me stop the ticking. And let me make actually just a new project. Okay, and just start over from scratch here. And I think actually on this, I need to switch because it's technically a different window. Okay, there we go. This one. Okay. So, what are the basic, what's fundamentally going to be all the parts of my computer? And let's just say Brookshire architecture for now. All right, Michael. Huh? How many bits? 4. Oh, okay. Well, all right. First off, what are the? Well, let's talk about the memory, right? What's the memory in Brookshire? How big is it? Yeah. Okay. 0 all the way to FF. So that's a total of 256 memory cells, which means how many bits do we need for data, and how many bits do we need for the addresses? It's 8 bits for each, right? Because 8 bits is 2 hexadecimal, 2 nibbles, right? And 1 nibble is exactly 1 hex character. Um, by the way, I realized the other day that all of this time I had been misspelling nibble. How do you spell nibble? No, you spell it Nybble when we're talking about computer nibbles. Like if you take a nibble of a sandwich, it's an Nibble. If you have a nibble of bits, then it's an Nybble. Like byte, right? Okay. I mean, Evan, the look on your face, like you thought you were going insane. Like, yeah.
I mean, you have to differentiate the two words.
Why is exactly the answer. Ah, you see what I did there, right? Okay. I'll be here all week. Huh? Actually, no, I didn't. Or you did. I didn't set you up for it, but you set me up for it, right? Okay. So, so our memory unit um, would need to have how many bits as its address width and how many bits as its data width. For Brookshire, it happens to be 8 for both of them. Okay, great. What is it for the MOS 6502? The address width is 16 bits, but the data bit width is still 8 bits. Okay. Now, the ARM ARM is obviously more complicated than this because um, how what different memory reads and writes are you capable of doing with ARM? Well, yeah, so like load and store, right? But when you load and store, like, is it possible to store a single byte? You can store byte, you can store half word, you can store word, and you can store double. Okay, which is strb for byte, strh for half word. We never used that. Str with a W for a word, which is 32 bits, and str with an X for double word, which is 64 bits, right? So you could interface with the memory module in widths of 8, 16, 32, or 64 bits, okay? Even though what each memory address contained, how many bits? Each individual address contained, it's actually 8, right? Right, so it's still 8, even though you can write 64 bits at a time, right? So the memory controlling unit for ARM would have to be a lot more complicated because it would have to say, okay, I just got handed 64 bits. I need to send the first byte to the first address, the second to the second, the third to the third, and so on, and not screw it up. Okay, so for whatever reason, and this is probably mostly for legacy design, when computers like, so let's think back to sort of the late 70s, right? So in the late 1970s, the processors of the day, okay, were uh, the Motorola 6800, okay, the MOS 6502, the Intel 8086, okay, which gave us the x86 architecture, and the Zlog Z80, which was actually compatible with the instructions of the Intel x86 architecture. Okay, so the story here, right, is that, um, and all of these processor families are in a way related. Okay, so Motorola, you guys know them, right? The 6800, great processor, wonderful. Bunch of engineers from Motorola were like, forget Motorola, and they broke off and started their own gig. And those guys ended up developing the 6502. Okay. Now, Motorola tried to sue the pants off of them. Okay. And in fact, in some sense, won because the 6502 was not their first processor. Guess what their first one was? How about the 6501? Right. And it was designed to be pin compatible with a 6800, which means you could take a motherboard that would, where you would plop in a Motorola chip, and you could buy their chip instead and plop it in, and it would work. Okay, so they would be compatible with any existing Motorola boards, but they could sell their own chip. right, for more monies and take that money away from Motorola. So Motorola sued the pants off of them for that one. Okay. Um, Zlog did the exact same thing with Intel, right? So uh, some Intel engineers broke off and started this company called Zlog, and their processor was the Z80 that was designed to be pin compatible with the 8086. Okay, now the Zlog Z80 um, did get used in some machines of in the 80s. Okay, it was actually relatively popular in the arcade world. Okay, so companies that built arcade machines sometimes used that. Um, let's see what else used it. So this one. How many of you guys have ever been to a Radio Shack? Yeah. Okay. Now they are. I mean, of course, they've gone bankrupt. How many more times than I have fingers? But uh, because like if you went to a Radio Shack 5 years ago, you'd walk in the door, and what would basically the whole thing be about? Selling you cell phones or cases and other stuff like that. Okay. In the 80s and the 70s, what was Radio Shack all about? Well, you could imagine that it started as radios, right? Hence the name, right? Okay, but it was really cool. Like you could go and so like even in the 90s or early 2000s, I was working on my computer, right? And I had like an intake air fan and it was really loud. So I wanted to slow it down so that it would still pipe air but not be quite so loud, right? Reasonable thing. Okay, nowadays what do you guys do if you want have this problem? Those of you who have desktop PCs. Yeah, exactly. Where your fans are plugged into the motherboard and you can do pulse width modulation and everything's cool, right? You can control it all through either the BIOS or software that interfaces with that in Windows. Well, children, we did not have these luxuries in the 80s and 90s, right? So your fans back then basically plugged straight into power coming out of the power supply. They weren't connected to the motherboard in any way. And what that meant was, yeah, they were the 4-pin Molex, which whoever designed those needs to be like beaten with a stick. Okay. Um, and those of you who know what I'm talking about know what I'm talking about. And if you don't, consider yourself lucky that you weren't traumatized by 4-pin Molex connectors. Okay. Okay. So anyway, um, uh, so I wanted to build something that would slow the thing down. Okay. So what I decided to do was to get a rheostat, which is a variable resistor. Okay, now this was in retrospect a horrible idea, but it would work, right? So if I put in some resistance, then there'd be a voltage drop, and therefore the fan would spin slower, right? Yeah, seemed like a good idea, or a current drop, not voltage drop. I mean, there would be a voltage drop because V equals IR, but whatever. Okay. Um, Lilith is over here screaming on the inside. Yeah. Okay. So why was this a horrible idea, though? Because a resistor does what? It gets hot. So this little part got, not melting things, but it did get a little toasty. Okay. Um, fine. Uh, but I'm like, where am I going to get a variable resistor? Right. So it's a resistor like with a dial basically so that you can adjust it. Well, where would you guys go today to get such a thing? You'd go to Amazon, okay, and or some other site, but essentially you'd go to the internet and you'd buy one of these things, and it would show up a week later. Well, what about if you want it today? Huh? What about if you want it in 10 minutes? Amazon Prime. Yes. Okay. Huh? Well, okay. Yeah. If you want it in 10 minutes, you can't just drive to Walmart and get one of these things, can you? But back then, you could drive to Radio Shack and get some of these components. It was great. You could walk in and be like, "Yeah, I need a blah 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 resistors," and they'd be like, "Okay, here you go. Here's a little baggie full." And it was kind of like if you need nuts and bolts of particular sizes, what do? You go to Home Depot, right? And you go to the nut and bolt aisle, right? And yeah, I'm repping because Evan here works at Home Depot. You find and then they're all sorted by their size, right? And if you need like 17 of some random bolt size, there's even the little trays, and you can buy, pick out individual bolts and nuts and washers and whatever you need, or you can buy the little baggies that have four of each of them or whatever, right? And they've got everything. They've got the metric sizes and they've got the imperial sizes. And you just get what you need. Well, Radio Shack was kind of like that, only not the size of a Home Depot, right? You could go in and buy different components that you might need to assemble, well, your radio or repair it. Well, okay, they weren't like that. I think most of it that was in the back kept organized, and you would tell the clerk what you needed, and then they would go get the thing. Or they'd be in little baggies, kind of like on the nut and screw aisle where, there's the bins, right? But y'all's bins stay pretty sane. I mean, I've never had a problem finding what I need there, even in metric. Huh? The fridge section? A refrigerator? They didn't have that, yeah. I mean, Radio Shacks were small, right? They were in strip malls. Well, that's, yeah, partly. Well, no, actually, no. That it's funny you say that because you'll notice that some retailers. So, for example, like Ace Hardware, right? Ace Hardware has had their lunch eaten by Home Depot and Lowe's because they're a lot smaller. Um, so, what have they done? They've tried to compete by having the Sears Hardware line, where they've got the washers and dryers and stuff, to get people in the door, and it works relatively well. Or like Best Buy, for example, they've done pretty well because, well, for many reasons, but even in the internet age, because you're not going to buy a washer and dryer on the internet, likely, right? You're going to go to the store because, or you're not going to buy a refrigerator on the internet, like a big fridge, right? It just doesn't work. It's like clothing, right? For the most part, you still want to go to a store and try something on. You like to try on your fridge? Okay. I don't want to know what you're doing with your fridge, bro. Okay. All right. But yeah, so you could go to Radio Shack and you could get these things. Okay. Now, why have I brought up Radio Shack? Because, um, well, so several reasons. So you remember hyper-specific memories? Well, one of my favorite memories as a kid was going to the mall with my mother. Okay. Now, how do ladies go to malls? I don't know if you guys go to malls anymore. They take forever because they go like, and let's say that the target is to go to the store and go to, I don't know, Express and buy a pair of jeans, okay, and leave. That how does a man do that? You walk in, you get the pair of jeans, and you leave. How do ladies do that? They go to every single store, and then they end up spending $800 on stuff, and they never actually went to the store they were supposed to. They go to every other one. Well, okay, not really, right? Um, so anyway, but my mother would do this where, like, let's say she wanted to shop for clothing. Well, if you're a 3-year-old child or 4-year-old child, this is not exactly entertainment. So what would she do? She would drop me off at Radio Shack. Yeah. And Radio Shack had electronic keyboards and all kinds of other really interesting things to a budding mad scientist. Okay. And so, you know, she would leave me at Radio Shack and I would be entertained and talking with the employees and playing with all their cool stuff. And then she'd come pick me up. It was great. And we'd go get a cinnamon roll. okay, or whatever, right? Yeah. So, but yeah, you used to be able to go to Radio Shack and get these things. Now, in the 80s, when computers started to become things that the average person could afford to have at their home, I mean, they were still kind of pricey, right? So it was definitely a middle class and up kind of thing to have a computer at home. Um, Radio Shack and its, well, really its parent company, decided that they wanted to sell a line of computers. And this thing was called the Tandy Radio Shack TRS 80 because it used a Zlog Z80 processor. Okay. And these things, because the first batches of them didn't have the best quality control, were affectionately known as trash 80s. Okay. TRS 80s. Okay. And so a lot of people had Z80 processors in their first home computers because a lot of people had trash 80s. Okay, now, Commodore, the Commodore Corporation, which is what made the Commodore 64, the Amiga, if you've ever heard of that one. Um, my first computer was a Commodore 64 that used a 6502 processor. Okay, so long story though, all of those processors had 8-bit address, or so, excuse me, 8-bit data spaces, right? So each memory address would hold 8 bits. How many addresses were there? Well, let's take all of those guys. They were capable of addressing, I think it was basically a 16-bit width for all of them. So they could address 16 bits worth of stuff, which is 64 kilobyte, or yeah, kilobytes, right? 64K addresses, each one holds a byte. Okay. All right. So for some reason, we left the width of each memory address as an 8-bit quantity rather than making it 16 or 32 or whatever as we increase things. Now, in one way, that was probably good because ASCII, for example, is an 8-bit thing, right? So if we're using an 8-bit encoding, it's certainly convenient to be able to put one character in each memory address, right? Okay, but the address widths grew, okay, to the point where now, basically, what is our address width for modern hardware? Well, don't say it all at once. 64 bits. Okay, now we don't actually use all 64 bits worth of it yet, but the address width basically, right? So if you have an address, well, okay, like let's take this, right? You guys, if you want to printf something, you have to pass it the memory address of the format string, correct? Where does the format string fit, or the memory address for it? What kind of register does it go into? It goes into an X, and in fact, it goes into X0 because that's the format string spot, right? So the address of the format string goes into memory address X0, right? How wide is that? 64 bits. Okay, now a bunch of them at the front might be zeros, fine. Okay, but it's a 64-bit address space. Okay, what's the Brookshire address space? It's only 8 bits. Okay, all right, well, how time flies when you're having fun. Okay, so I think basically I'm ready to start giving you guys some things to build in Logisim. Okay, and like we were talking, I think before, like what's the whole idea here? Build a component and abstract it to a magic box. Build another component, abstract it to a magic box. And then let's say for the ALU, it'll be magic boxes inside magic boxes. Okay, so what we're going to build up to is you guys basically constructing the full Brookshire ALU by building each of the components. An adder, a and/or an XOR, the full barrel shifter, we started that today. Okay, and then the last thing, which I probably should have mentioned, was how to check equality, but we'll talk about that one next time. Okay. All right, does it make sense kind of where we're going with this? Yeah? Okay, cool. see you guys on, well, today is Thursday, right? So have a good weekend, and I will see you next time.